Welcome to National 5 Computing Science. This is our first unit called Computer Systems. In today's lesson we will be looking at data representation. As always, we have some learning intentions, which are as follows. We will learn how positive integers are represented in binary. We will learn how positive real numbers are represented using the terms mantissa and exponent. We will learn how to convert from binary to denary and vice versa. We will learn how extended ASCII code, 8-bit, is used to represent characters. And we will learn how vector and bitmap graphics are used to represent images. Again, we have some success criteria. I can describe how positive integers are represented in binary. I can describe how positive real numbers are represented using the terms mantissa and exponent. I can convert from binary to denary and vice versa. I can describe how extended ASCII code, 8-bit, is used to represent characters. I can describe how vector and bitmap graphics are used to represent images. I can identify and describe vector graphic objects and attributes. As always, we should look at our success criteria throughout the lesson to benchmark our progress. Before we move on with the lesson, let's have a small definition. A bit, or a binary digit, this is the smallest unit of measurement in binary. This would be represented using a 0 or a 1. When computers use and operate on data, it is represented in binary or machine code. Machine code is the native language of a computer system, and it's written in bits. Again, bits can be either zeros or ones. All text, numbers, images, sounds, and all other types of information within our computer system are represented and stored in this format. Let's have a look at some units of measurement. As mentioned in our definition, the smallest unit of measurement in binary is 1 bit, a binary digit, a 0 or a 1. 1 byte of information contains 8 bits. We then move up our units of measurement 1024 times. So 1 kilobyte would be 1024 bytes. 1 megabyte, 1024 kilobytes. 1 gigabyte, 1024 megabytes. 1 terabyte, 1024 gigabytes. And 1 petabyte, 1024 terabytes. So in conclusion, 1 bit, zeros or ones, 1 byte is 8 bits, and then we use that magic number of 1024 as we progress up the units of measurement from kilobyte to megabyte to gigabyte, terabyte, and finally petabyte. Let's look at representing denary numbers. Denary numbers are relatively simple to represent in binary. It's possible to convert whole denary numbers or integers to binary and back quite easily by hand. Both of these conversions make use of a table representing a group of bits. At National 5, we always use 8 bits for this. Now let's look at a denary to binary conversion example. We'll convert the number 85 into binary. The bottom row will contain the value of each bit. They're all being initialized to 0 at the moment. The top row will contain the denary value for each of the bits. In this case, we have ones, single units. That's the least significant bit because it is the lowest denary value. 2, 4, 8, 16, 32, 64, and 128 and that gives us 8 bits in total. And these are the values that each of these bits will represent. 128 will be known as the most significant bit because it represents the highest denary value within our 8 bits. Now let's move on with our conversion. We start the process with the most significant bit. And we ask, does 128 go into 85? The answer to this is no, so we set this bit to 0. We then move along the line of bits and we ask, does 64 go into 85? In this case, it does. We set this bit to 1, but this also gives us a remainder of 21, and this is the value that we use moving forward. We then go to the next column. We ask, does 32 go into 21? In this case, no. We set the bit to 0 and we move to the next column. Does 16 go into 21? In this case, yes, it does. And we set the bit to 1, giving us a remainder 5. We move to the next column. Does 8 go into 5? The answer is no. Set that to 0, moving forward with our value of 5. Does 4 go into 5? The answer is yes, and we set that bit to 1. Okay, and that gives us a remainder 1. So 4 away from 5 gives us 1. And we move forward with that value to the next column. Does 2 go into 1? Again, we set that bit to 0 because it doesn't, leaving us still with a value of 1. Moving to our final column, does 1 go into 1? Our answer is yes, and we set that bit to 1. After our conversion has taken place, we can see that this gives us a binary value of 01, 01, 01, 01. Let's move on with our second example. We'll be converting binary numbers to denary this time. Let's convert the number 01, 01, 01, 01. We'll fill the binary number in to be converted in the bottom row. We will then add all the denary values where the bit is set to 1. In this case, we have 64 plus 16 plus 4 plus 1, giving us a total of 85. So 01, 01, 01, 01 equals 85. It's just the reverse of the first example we showed. Let's now look at how the computer stores and represents real numbers. It uses a technique called floating point representation to represent real numbers, or numbers with a fractional component to them. Floating point numbers are made up of 2 parts called a mantissa and an exponent. It's in this way that floating point representation is similar to denary standard form or scientific notation. In the floating point representation technique, the decimal point is always assumed to be at the start of the number or before the most significant bit. In this case, we have moved the decimal point 5 places to the left to move it in front of the most significant bit. This means that we do not need to store the decimal point because it's always presumed to be at the start of the number. It also provides us with our mantissa, which is 1500711 in this case, and our exponent, which in this case is 5. The larger the binary number used in the mantissa, the more accurate that number will be. And the larger the binary number used for the exponent, or the more bits used for the exponent, the larger the potential range of numbers we are able to represent will be. So if we add more bits to our mantissa, we increase accuracy. If we add more bits to our exponent, we increase the range of numbers we can represent. Let's now look at how the computer stores and represents text. We're going to look at extended ASCII. This is a common and universal format for representing text in binary. This method allocates each character with a unique 8-bit binary number. Extended ASCII can represent a total of 256 characters, 2 to the power of 8. The first 32 8-bit binary numbers are allocated to something called control characters, such as your spacebar or the enter key. The remaining numbers are allocated to printable characters such as capital A to Z, 0 to 9, brackets and punctuation marks, etc. Using only 8 bits for extended ASCII means that we can only represent 256 characters. Ultimately, this can be insufficient to represent multiple languages. An alternative method is the use of Unicode. Unicode uses 16 bits and can represent 65,536 characters. We'll learn more about Unicode in the higher course, but it gives us something to compare and contrast against. As mentioned earlier, to represent a larger range of characters, Unicode uses 16 bits to represent each character. Unicode therefore requires much more memory than extended ASCII. But the first 256 values in Unicode are the exact same characters represented in extended ASCII. This makes it easy to convert between extended ASCII and Unicode. Let's now discuss how the computer stores and represents graphics. The first graphic we will look at is a bitmap graphic. Graphics can be represented in binary using a bitmap format. We see an example of this in the graphic on the left hand side. We see the image and the bitmap of that image to the right. A bitmap graphic represents an image using a grid or 2D array of pixels. Each individual pixel or picture element is stored and is allocated a binary value, which represents the colour associated with that pixel. For example, the binary value 0 could represent black, and the binary value 1 would represent a white pixel. When it comes to colour graphics and colour bitmaps, these binary values get much more complex. Let's look at this example. This image is a black and white or monochrome image. It has 8 pixels by 8 pixels. We are using 1-bit colour depth for each pixel, which means we use either a 1 or a 0 to represent each pixel. Therefore, the image requires 64 bits of storage. If we remember back to our units of storage, a pixel or a bit in this case, a 0 or a 1 is the smallest unit of storage. There are 8 bits within a byte of storage. So in this case, we have 8 bytes. If this image contained colour, additional bits would be allocated to every pixel to represent the colours. For example, in a true colour photographic image, we would use 24 bits per pixel. This would significantly increase the file size of this image. Another type of graphic is a vector graphic. Rather than storing each individual pixel like a bitmap, a vector graphic uses an alternative method of representation. A vector graphic is stored as a list of attributes that help the computer to describe and re-represent that image or object. Common vector objects are rectangles, the ellipse, the line, and the polygon. Each vector object will have an associated set of attributes. Examples are coordinate points x and y, line colour, fill colour, line style, line thickness, fill pattern. These are all examples of attributes. In this example we have an ellipse. This would be represented using coordinate points x and y, a line colour of orange, and a fill colour of yellow. There are many other attributes that would be associated in drawing this vector. These are just some examples. All of the shapes we previously mentioned, the rectangle, line, and polygon, would have similar attributes, with the exception of the line, which won't have any fill attributes. Thanks for joining us for this lesson. Please make sure to regularly visit our faculty YouTube channel, EASCII Business Computing Science, and subscribe for more information.